Professor of Organic Chemistry at the Department of Chemistry and Industrial Chemistry of the University of Geneva. So I allow the presentation to start. Okay. So the title of my lesson will be Sustainable Organic Synthesis, Shifting from Oil to Biomass Starting Material. Okay. So I don't know how is your knowledge of organic chemistry, so I apologize if for some of you is some things that I am saying now are quite trivial. But the first thing to say about circularity of organic chemistry is to explain what is organic chemistry. Organic chemistry is a branch of chemistry that studies carbon-containing compounds. So carbon is the only element among the 94 elements found in nature that is worth a specific topic of chemistry dedicated to it. And why? So maybe one can think that it is because it's the most abundant one on the Earth's surface. No, it is not true. Actually, carbon is only the 15th as the abundance on the Earth's surface. And there are several elements that are more abundant than carbon, like, for example, oxygen, silicon, aluminum, iron, calcium, sodium, and so on. So the real motives for carbon being so important to being worth of a specific branch of chemistry dedicated to it are these two. These are actually strongly interconnected. The first reason is that biological life is based on carbon compounds. And the second reason is that only carbon is able to generate, by combination with few other elements, an immense number of different molecules. So there are much more molecules based on carbon than on all the other 93 elements. And these two reasons are strongly interconnected because everybody think that life could exist only thanks to the great chemodiversity of carbon compounds. Okay. The astonishing potential chemodiversity of organic chemistry can be understood looking at some numbers. In organic compounds, carbon is always present, hydrogen is nearly always present, and often we have oxygen and nitrogen, and less often sulfur and phosphorus. This in natural organic compounds. Only very seldom natural organic compounds contain halogens, such as chlorine, bromine, iodine. Someone has calculated how many different molecules are possible using only carbon, hydrogen, oxygen, nitrogen, and sulfur, and limiting to molecules not too big, with molecular weight under 500 Daltons, so excluding all macromolecules like proteins, nucleic acid, and so on. So they calculated that the number of possible molecules, as possible, I mean molecules that should be stable, so no problem in preparing them and having them stable. This number is 10 elevated at 63. This is a very, very big number. Just to give an idea, the organic molecules that are known today, so known means that they have been reported in some scientific papers with all characterization and so on, is about 10 at the 8th, so 100 millions. So this is a very, very short percentage. And to give an idea, all the known inorganic molecules that are all the molecules containing all the other elements are only 6 per 10 at the 5th. To give an idea, often the possible molecules are considered as a space, a chemical space. So we have explored only a very small part of the chemical space. To give an idea, I try to calculate how much space we have explored on a geographic comparison compared to the whole surface of Earth. Well, we have explored less than the tip of a needle. So really, the compounds we know today are only a very, very small part of all possible compounds. But organic chemistry is not only the chemistry of natural substances. This is a brand new discipline born around 1830. And since then, chemists have found a way to synthesize not only natural organic compounds, but also artificial organic molecules, molecules that are not present in nature. And many of these, several of these molecules have found interesting application. In doing that, chemists have been able to add also other elements that are rare in nature, like, for example, chlorine, or even never found in the living beings, like fluorine or silicon. The immense chemodiversity potential of organic chemistry has allowed the obtainment of molecules that have found practical applications in many fields. And so nowadays, most of industrial chemical products are organic products. Organic compounds are all around us as single molecules or as polymers, materials, and they are central to economic growth and are foundational to the fields of biochemistry, biotechnology, and medicine. So organic chemistry is very important, as demonstrated by the number of organic chemists that are working all around the world. Probably organic chemists in general are even more than inorganic chemists. Organic chemistry is everywhere. There are a lot of application. We can divide application of organic chemistry into big sectors. Biological application is not surprising that organic molecules can have biological applications because they are similar to the molecules that are fundamental for the life of living beings. So drugs are organic molecules, but also pesticides, fertilizers, cosmetic products or products for cleaning, scents, flavoring, food supplements, or disinfectants. All these molecules have somehow a role for some biological organisms. But organic chemistry has found also a lot of application in non-biological fields. For example, for structural organic materials, think at plastics, rubbers, textiles, and so on. And also detergents, products for cleaning, dye stuff, paints, pulp and paper as additive, but paper is organic actually, but also additives used for paper. And then a lot of materials for construction, coatings, glues. And more recently, organic chemistry has found interesting application in functional materials for electronics. For example, you know that OLED, in OLED, this acronym O means organic. Organic solar cells and also functional materials with photochemical or photoelectronic properties and sensors. All these applications have a great impact on chemical industry, and every year hundreds of millions of tons of organic molecules are produced by the chemical industry. But the question is, all these organic material, where do they come from? For the most part nowadays, they come from oil. Oil is the main source for the production of organic molecules, organic polymers that we are using in our day life. But there is a big problem. The big problem is that oil is not renewable. So the deposits of oil around the world have taken millions of years to be established. Now we are depleting these deposits, and sooner or later they will oil will end up. So sooner or later we must find a replacement for it. And then there is another problem. Since oil is not a renewable source, at the end of its life, even if it is used not for producing energy, but for producing chemicals, In the end, all these chemicals sooner or later will get into CO2, carbonic anhydride. And so they will contribute to the present imbalance of the carbon cycles. Nowadays, as you surely know, we are sending in the atmosphere more CO2 than the Earth and the sea and the oceans are able to absorb. And so this imbalance is creating a constant increase of carbonic anhydride concentration in the atmosphere and causing the global warming effect. So, as a matter of fact, only 15% of the oil every year is used for the production of organic chemicals. The rest is burned to produce energy. So 15% may seem not too much. So surely the main focus must be on reducing the 85% that we are using for producing energy. But 15% is not so little after all. And so I think that research must start to think how to find ways to obtain the organic molecules we need, not starting from oil. So, as I told you, organic synthesis starting from oil is not circular. Oil is composed mainly by hydrocarbons, and among hydrocarbons, the main part is given by alkanes. Alkanes have a general formula CnH2n plus 2, and so they are hydrocarbons that are molecules that are formed only by carbon and hydrogen. As I told you later, in a few minutes, in order to obtain useful molecules for our application, we need to oxidize the components of oil with the addition of oxygen, but also nitrogen. And this may be done using oxygen. This is not a problem because we are very rich of oxygen. Organic compounds with application in various fields may be recycled. That is surely positive, but in the end, they will arrive, even if they are recycled, sooner or later, they will arrive at the end of life. At the end of life may be incineration, that is better, but this produces CO2. But also, if they go into landfills, sooner or later, they will become CO2. And the CO2 is not recycled. This is not a circular economy because oil is not produced in few years from CO2. It takes millions of years. The alternative is to use biomass. Biomass is a mass of organic compounds produced by organisms that are living nowadays. So the process is similar. The difference is that biomass usually is more oxidized than alkanes, hydrocarbons. And so we will need often to perform not only oxidative, but more often reductive processes to obtain molecules containing oxygen. That is, oxygen is usually already present in abundance in biomass, but we may wish to add nitrogen or other elements. And at the end of life, in any case, they will turn out into CO2. But the big difference is that CO2 can be absorbed by plants and then return to biomass. So this economy is circular. So the advantage of using biomass-derived organic compounds, the main advantage is that they are renewable. So the CO2 that we produce at the end of life can be converted back into biomass in a few years because CO2 is absorbed by the same plants that we have used for, same plants or organisms that we have used for producing biomass. So this is the alternative. But this is not easy because we have to set up a completely new synthesis of organic compounds. I will show you the difference. Oil is formed by hydrocarbons, that is, molecules that contain only carbon and hydrogen. In order to obtain the molecules that we are commonly used, we need to add other elements like oxygen, nitrogen, sulfur, and maybe chlorine. I show here in this slide two examples of two drugs, two very popular drugs, acetylsalicylic acid, that is aspirin, and diclofenac. As you can see, acetylsalicylic acid contains 4 oxygens. Diclofenac contains 2 oxygens, 1 nitrogen, and 2 chlorine atoms. So if we start from oil, surely we have to add other elements like oxygen, nitrogen, chlorine. But if we start from biomass, biomass is rich of oxygens. The typical product of biomass is glucose. Glucose has 6 oxygens. And another product that I show here is ferulic acid, which can be derived from lignin. Also, ferulic acid is rich of oxygens. In this case, in order to obtain the products that we need, we must sometimes remove oxygens and maybe add the nitrogen, sulfur, or chlorine. So it is a completely different synthesis. From oil, we start from simple, just carbon, hydrogen, and go into the direction of complex. Starting from biomass is the opposite. We have more complex molecules that we need to simplify. And I will show you some selected examples to demonstrate that. An interesting case about the organic chemistry starting from oil is the chlorine case. The element chlorine is quite widespread in nature, but always at the chloride anion. So the oceans are rich of sodium chloride, so we have a lot of chlorine. But on the contrary, the biatomic molecule Cl2 is not found at all in nature. It is a poisonous green gas, and until 1992, it could be found just in research laboratories. So it was an academic curiosity. Chlorine is quite reactive, and thus they knew already that it is one of the few reagents able to react easily with hydrocarbons. Hydrocarbons are poorly reactive. I'll show you in a minute, but they can react relatively easily with chlorine, introducing chlorine atom. What happened in 1992? In 1892, the chlorine caustic soda process was conceived. This is an electrochemical process where, by consuming energy, electric energy, it is possible to convert two very cheap molecules, sodium chloride and water, in practice seawater, into chlorine gas, hydrogen, and sodium hydroxide. Sodium hydroxide and chlorine are obtained into different containers, so they are not mixed. Interestingly, this process was conceived for the need to produce caustic soda, that is sodium hydroxide, not for the need to produce chlorine. In the first time, the people in the industry didn't even know what to do with chlorine. And I read that they even liberated it in the air, not knowing what to do with it. That was not very, very good from the pollution point of view, but in the 19th century, they were not very much concerned about pollution. But later, in few years, they understood that it was silly to throw away chlorine. And so they looked for application of this reagent. A simple and very popular application is that if you mix chlorine with sodium hydroxide in water, you obtain sodium hypochlorite, that is bleach, candeggina in Italian. So that is very useful for as disinfectant, for cleaning, whitening clothes, and so on. But also they understood that chlorine was very useful to functionalize alkanes or in general hydrocarbons. I will show you an example. Oil is composed mainly by alkanes. Alkanes are hydrocarbons where there are only single bonds, so carbon and hydrogen. And it would be very useful to be able to convert an alkane, here I show just as an example butane, into an alcohol, adding an oxygen. This is in principle possible, but there is a big problem. Oxygen is a very slow oxidant. So in order to activate this reaction, you have to warm to a very high temperature, at least 500 degrees. But at that temperature, the reaction does not stop at the level of the alcohol, and everybody burns and goes to give CO2, carbonic anhydride. For those who are not practical with organic chemistry, I will show here this formula shows all the atoms, carbon, hydrogen, oxygen. But often in organic chemistry, we use a simplified formula that I like more, obviously, because it's easier to be drawn, where you see we draw a zigzag chain where carbons are supposed to be here. So here is a carbon, a carbon, a carbon, a carbon, and also hydrogens are implicit. So you have just to draw the chain of carbon atoms and put oxygen, nitrogen, and the other heteroatoms, which are never implicit. So this reaction is not possible, but on the contrary, it is possible to use chlorine gas to introduce a chlorine atom into an alkane to obtain an alkyl chloride. And then by simply treating this alkyl chloride with sodium hydroxide, it is possible to obtain an alcohol, or treating it with ammonia, it is possible to obtain an amine. So chlorine was found to be a very good intermediate to introduce chlorine into alkanes or hydrocarbons in general, and then substitute the chlorine with oxygen or nitrogen. So a way to functionalize hydrocarbons. I must say that the problem is that alkanes are poorly reactive. Sometimes they are called also paraffin. Paraffin comes from Latin, parum affinis. That means they are not so they have little affinity with other elements. So in other words, they do not react very easily. But meanwhile, by synthesizing many chlorine-containing compounds, chemists have also found that chlorine-containing compounds can be useful, can have several applications. For example, in drugs. As I told you, chlorine is present in organic natural compounds, but not very often. But it's quite often present in drugs. Here I show just 3 examples. Clopidogrel, that is a platelet agglutination inhibitor. Gefitinib, that is a new a smart anti-cancer drug, being an inhibitor of tyrosine kinase receptors, and ezopiclone, the used for the treatment of insomnia. These are just 3 examples of chlorine-containing drug. But as I read in this interesting review, there are more than 250 approved drugs containing chlorine. And chlorine is the 5th element most frequent in drugs after carbon, hydrogen, nitrogen, and oxygen. So for some reason, they found that chlorine can be very useful in drugs. But also in materials. Here, for example, I show that by treating ethylene, which is a typical oil product, by cracking of oil with chlorine, it is possible to obtain vinyl chloride, which gives a polymer, polyvinyl chloride, which is very useful. Polyvinyl chloride is quite used, for example, for tubing. And think that 30% of the annual production of chlorine Cl2, the bioatomic molecule, is used for PVC production. And they also found a lot of chlorine-containing pesticides, insecticides. The most popular one is probably DDT. Here is the formula of DDT. DDT was found to be a strong and efficient insecticide, relatively low toxicity for man, and was used in the 40s and the 50s of the last century for defeating malaria in large parts of the world, because obviously malaria is brought by flies. And think that this discoverer, Paul Hermann Müller, has received in 1948 the Nobel Prize for medicine, not for chemistry, for the invention of DDT. But what happened? In the 50s and in the early 60s, in the United States, many farmers thought that using a massive using of these pesticides could be useful in increasing the yield of the crops. But a biologist, Rachel Carson, published in 1962 the book titled Silent Spring, where she described that she found that these pesticides going into water, not being biodegradable, could cause problems to, especially to the aquatic birds, because they act as endocrine disruptors, so they interfere with the action of hormones, especially sexual hormones. So chlorinated compounds may have some ecological problems, a bad footprint in the environment, and they are poorly degradable. Also, chlorine-containing compounds do not burn very well, and in particular, one of them, this one shown here, that is tetrachlorodibenzoparadioxine, often called just dioxin, is terrible because it does not burn at all unless at very high temperature. And so if you burn at low temperature something containing chlorine, you obtain some dioxin that is toxic, cancerogenic, and so on. So chlorine has some problems, but I was wondering, this is an opinion, so take as you like. My reasoning was that I show you that we have explored just a very little portion of the chemical space. So the molecules we have found useful that we use every day are the best ones. We cannot know. We had just explored a very little. It's like if you go searching for mushrooms in a very big forest, you explore just one very little space. You don't find mushrooms, or you just find someone. You never know if in other part of the forest there are a lot of mushrooms or not. And so we are not sure that the useful molecules we have found are the best ones. Maybe they are not the best ones. They've been only the simplest to be found. Here, science, says Noam Chomsky, is a bit like the joke about the drunk who is looking under a lamppost for a key that is lost on the other side of the streets. And the policeman asks him, but are you sure that you lost the key here? No, I'm not sure. So why are you looking for it here? Because here there is more light. So in science, it's the same. Probably we have synthesized the molecules that were easier to synthesize. So for this reason, we have prepared a lot of molecules containing chlorine. But if we had started not from oil, but from biomass, maybe we could have obtained different molecules, maybe better. I don't know. This obviously, we never know. So the advantages of using biomass instead of oil and starting materials are several. The first one, obviously, this is sure, this biomass is renewable, and thus we can really set up a circular economy starting from biomass. But the second advantage is starting from biomass, we cannot necessarily synthesize the same molecules we have obtained starting from oil. Maybe we can find new molecules that are better than the old ones. First of all, they have more chances to be biodegradable. As Professor Arato said, it is not necessary, it is not always true that biomass-derived molecules are biodegradable. But since they are coming from organic, natural organic compounds, they have anyway more chances to be biodegradable. And in general, they will leave a lighter footprint on the environment. And a first advantage is the valorization of biomass can create synergies and economical advantages to sectors such as agriculture, fishery, wood industry, and so on. So product waste of these economic sectors can become a value for a new organic chemistry starting from biomass. So adding an economical value to these sectors. And this in my opinion, it could be very important, especially for those countries like Italy that do not have big deposits of oil or natural gas. But we have fields, we have a very nice territory where we can develop a better, more complete agriculture, or we have the sea for the fishery, and if we are able to exploit the waste of fisheries that will be an economical advantage. Obviously, there are also several challenges to be faced. First of all, biomass is a complex mixture of substances, and they are highly functionalized, more difficult to purify than oil. With oil, a distillation is usually enough to separate the components, and with the natural substances in biomass is not so easy. Then the main biomass components are highly functionalized, so the synthesis must proceed from complex to simple, whereas from oil it proceeds from simple to complex. And in general, to proceed from simple to complex is easy. The cost of production may not be competitive if oil continues to remain so cheap. This is a big economic problem. The day oil will cost 5 times more than now, biomass will become economically an advantage. So, although from the sustainability point of view and the circular economy point of view, biomass is better. Unfortunately, if the cost of the final material is much higher than the one obtained from oil, this may be a problem. Then we must be careful not to distract agriculture or aquaculture from the main goal, that is to feed an always increasing world population. And another problem is that if we use land biomass, typical land biomass is mainly composed of carbohydrates, triglycerides, and lignin. All of them contain a lot of oxygen, but no nitrogen. And for example, most drugs contain nitrogen, so we must find a way to introduce nitrogen in our compounds. In few words, a completely new organic synthesis must be developed. When I was a student in the 20th century, the challenge was, are we able to synthesize any molecule? So the most famous organic chemistry were fighting in order to be the first to synthesize a very complex molecule. In 30, 40, 50 steps, it was not important how, it was important to reach the target. Now, in the 21st century, the challenge has changed, in my opinion. Now it has become, how can I synthesize the molecules I need in a more sustainable and green way, starting from renewable sources? So the focus is no longer on the target, but on the way we are obtaining that target. Okay, biomass. Biomass is typically divided in the first generation, second generation, third generation. The first generation biomass has been the first one to be explored and comes from typical agricultural product. For example, plants rich of sugars, starch, like corn, especially corn, which is probably the cheapest cereal. But this was a problem because when corn started to be used, especially to produce biofuels, there was an increase of the world price of corn, and this was dramatic for poor countries where they hardly succeed in buying cereals to live. And this was a problem, because the problem is that first generation biomass is in competition with food. Here, there is a cartoon with a poor child asking for some corn, and the farmer say, oh no, I don't have any more corn, I can give you some ethanol obtained from corn that was used, the bioethanol, for as a fuel. And also, oilseed crops were important because they are a source of triglycerides. So, for example, sunflower, soy, rapeseed, palm. But also in this case, there were some problems because maybe the cultivation of these plants distracted the farmers from other crops that were more important for the sustainability of their population. So we now focus mainly on second generation biomass. Second generation biomass is something that is not in competition with food and can turn waste into a resource. For example, there are places in the world, also in Italy, where it is not possible to cultivate typical crops. So they are called not arable lands. In these not arable lands, often dry with few water, there are anyway some plants that are growing and they are producing biomass. So these plants, I'm not an expert of botany, maybe some of you are. I here quoted some of them, like the Jatropha or the Miscanthus, that can be used for this application. Another second generation biomass is wood. Wood is forest, usually in countries like Italy, grows in places where it is not possible to cultivate corn or wheat or other things. And so it's not in competition with food. Forests are regenerated. You can cut trees every year and without depleting the possibility to absorb CO2. And then also waste from agriculture. I quoted here the olive mill wastewaters, or also urban waste, food. There is a lot in cities of food that becomes waste. Third generation biomass is somehow related to the sea. And this is quite interesting because the sea is a very big possibility, although I must say, at least for the production of commodities and chemicals for synthesis of organic compounds, has not been explored very much till now. So in this lecture, I will speak mainly about land biomass. But the sea is quite interesting for many reasons. Surely it is not in competition with food because it does not use arable land. Then the accessible volumes is enormous. 70% of the Earth's surface is oceans and seas. So you have a lot. You don't need to build roads to go to the various parts of the ocean or the sea. You don't have to go up mountains, passes, and so on. No need for fresh water. The sea is already plenty of water. And maybe an interesting thing that maybe not everybody knows, the composition of organic matter, so of biomass, is much different from land. The reason is that the composition of organisms in the sea is much different from the land. Think that on the land, the ratio in kilograms, in weight, the ratio of producers compared to consumers is 5:1. Producers are the organisms that are able to do the photosynthesis and produce organic matter. The consumers are animals, for example, or bacteria, those who are not able to produce organic matters, but they only consume. The ratio is 5:1 in land. In the sea, the ratio is opposite. Is 5:1 in favor of the consumers. This is really astonishing, amazing to me. One can wonder how can it be possible that consumers is 5 times more than producers. The reason is that the rate of consumption by consumers is much lower in the sea than on the land. But this means that also the composition of organisms is quite different. In land, 90% or weight of biomass is plants. In the sea, plants is only a small percentage, you see, and this sea is dominated by protists and animals, but also bacteria. So due to this different composition, consumers have more nitrogen than producers, and so there is more nitrogen in the sea. And so this could be an interesting hint to because, as I will show, the typical biomass from land contains no nitrogen. By now, the main application of third generation biomass of the sea has been algae. Algae can be cultivated. They can produce a lot of interesting organic materials, especially triglycerides. Algae can be very rich in triglycerides. They can be used for fuels, like, for example, biodiesel, but they also produce interesting organic molecules. And I think it is worth exploring more these organic molecules as starting material for organic synthesis. And then another possible application is the use of waste. In fishery industry, there is a lot of waste, and all these waste contain valuable organic materials that can be in some way extracted and can be used as starting material. But as I told you, probably we are less advanced in this field than on using land biomass. So in this lecture, I will concentrate mainly on the use of land biomass. On land biomass, land biomass is dominated by glucose. Glucose is present not as glucose itself, but as polymers. So cellulose is a polymer. Glucose is the most abundant natural organic compounds in the world. Is the most abundant component of biomass in many plants, also in wood. The main component is cellulose or other glucose polymers like hemicellulose. I will do some reasoning about glucose, especially regarding the oxidation number. What is the oxidative state of carbon? First of all, the oxidative state of an element can be defined by the oxidation number. In organic molecules, the element that can be more or less oxidized is essentially carbon, because hydrogen and oxygen have always the same oxidation number. Hydrogen is always +1 and oxygen is always -2. So in order to calculate the oxidation number of carbon, we must take in mind that if the molecule is neutral, the sum of all the oxidation numbers should be 0. So in glucose, we have 12 hydrogens, that is +12, and 6 oxygen, that means -12. So carbon is 0. The overall number, the overall oxidation numbers of carbons is 0, and so the average oxidation number of carbon is 0. To make a comparison, we can take a typical component of oil, so an alkane. I've taken a light alkane, but it's the same with longer alkanes, hexane. In hexane, we have, as you can see, 6 carbon and 14 hydrogens. So the overall oxidation number of carbon is -14, and the average oxidation number of carbon is -2.33. So alkanes are less oxidized or more reduced than glucose. Think that the highest oxidation number of carbon is the one present in CO2, carbonic anhydride, where the oxidation number of carbon is +4. So what happened when we eat food containing glucose or polymers of glucose? What we do is to convert it into energy, converting all the carbons into CO2. So we oxidize glucose from 0, each carbon, to +4. In order to perform an oxidation, we need an oxidant. And the oxidant that we use is oxygen. We are rich of oxygen, it is in the air, so we can use oxygen, and aerobic organisms like us simply burn glucose to give water and CO2. This is obviously not useful from the production of starting material for organic synthesis. But a big opportunity is given by anaerobic organisms. Anaerobic organisms live in the absence of air, so they don't have oxygen as oxidant. They don't have an oxidant, so they are anyway compelled to metabolize glucose to produce energy, but this metabolism should be redox neutral. So it's less efficient. They produce, for each molecule of glucose, they produce much less energy than aerobic organisms produce, but they must find a way to set up a process that is redox neutral. These processes are called fermentations. The most famous fermentation of glucose is the alcoholic fermentation, where glucose is converted by S into a molecule of glucose is converted into 2 molecules of CO2, so there is an oxidation, +8, but also 2 molecules of ethanol, so the carbons are in part reduced, -8. So the reaction is redox neutral. But glucose is converted from to compounds more oxidized, CO2, and to compounds less oxidized ethanol. So, in other words, we can use fermentation by suitable microorganisms, anaerobic microorganisms, to obtain other organic molecules, not only CO2, that is useless for our organic synthesis, but for example, ethanol, which can be a starting material for some synthesis. But fortunately, we do not have only alcoholic fermentation. There are plenty of microorganisms, and they perform different kinds of fermentations. And also, we can modify them by genetically engineering biotechnological methods to force microorganisms to do what we need. So this is a great opportunity. I will show you an example. This is an example on how these two companies, Versalis and Genomatica, have explored a way to obtain a typical oil product, very useful, obtaining it from biomass. This product is butadiene, 1,3-butadiene. 1,3-butadiene is a monomer that is polymerized to give polybutadiene, that is a rubber that is used in many applications, but for example, is one of the components of the common tires we use. Butadiene is a hydrocarbon, so it's very logical to obtain it from oil. It's much less logical to obtain it from glucose, because glucose has 6 oxygens, and in butadiene there are no oxygens. So how can we chemically succeed in removing all this oxygen? I think it is nearly impossible, but fortunately microorganisms can do that. So they have found microorganisms optimized by genetical modification that are able to convert glucose into a less oxygenated molecule that is 1,3-butanediol plus CO2, obviously, because we lose 2 carbons. And 1,3-butanediol at this point can be simply eliminated. There can be a simple elimination of 2 molecules of water, and this can be done by chemical reaction with appropriate catalysts, suitable catalysts, to give butadiene. So this is an example how to obtain a typical oil-based polymer, but starting from biomass. Obviously, this polymer is not different from the one we obtain from oil. But since we start from biomass, the production may be seen as circular. So the starting material is renewable. As a starting material, we obtain glucose. Where glucose comes from? Okay, we don't find glucose very easily in nature. What we find in very high quantity are lignocellulosic feedstocks, so wood, agricultural waste, urban solid waste. So chemical engineers have developed very suitable methodologies through chemical or also enzymatic processes to break down the polymers of glucose, especially cellulose in this feedstock, to obtain glucose. And then fermentation goes on. But we don't even need to obtain glucose in a very pure form, because microorganisms can work also on mixtures, on dirty glucose. Several years ago, I did in the lab some reaction using baker's yeast as a reagent, and I need to give something. And we had a breakage of our coffee machine in the institute, and all the coffee contaminated sugar that we use for coffee. So the sugar was going to be thrown away. I said, no, give me the sugar I will use for my yeast. So for yeast, you don't need to use pure sugars. Also, dirty mixtures are okay. So this is another advantage of using microorganisms. Okay, but choosing the appropriate microorganism, we can succeed in obtaining other kind of compounds, starting from the same starting material, that is glucose. For example, they studied the production of succinic acid. Succinic acid is a 4-carbon compound which has several applications. Is compound of some polymers, but is also used as starting material for the production of other chemicals. And typically, succinic acid is obtained from oil. So I will show a typical pathway from oil. That means oxidation, because oil is the alkanes are the most reduced organic compounds. So butane, sorry, here is written in Italian, but butane can be oxidized by oxygen and catalyst to give maleic anhydride. Unfortunately, also in this case, we cannot stop a succinic anhydride. This is necessary to oxidize more and then to reduce using hydrogen. Succinic anhydride is just an anhydride of succinic acid, so a simple hydrolysis can give succinic acid. This is the typical traditional synthesis from oil. But from glucose, they have developed, also in this case, using genetically modified microorganisms, a very interesting fermentation where, contrary, you see in alcoholic fermentation and also in the fermentation I've shown before, although I didn't write that, you typically produce CO2. So glucose is in part oxidized to CO2, in part reduced. Like in alcoholic fermentation, where ethanol is produced by reduction and CO2 by oxidation. But in this interesting fermentation, not only there is no CO2 formation, but even one molecule of CO2 is absorbed. So glucose, 6 carbon, plus CO2, 1 carbon, are mixed together in this fermentation, giving succinic acid, acetic acid, formic acid. So 3 building blocks for an overall number of carbon of 7. And the overall is C7H12O8. That is exactly the sum of glucose, C6H12O6 plus CO2. So no CO2 formation, but even consumption of CO2 to afford this interesting building block. So this is a very smart process to convert the glucose without production of CO2 or with absorption of CO2 to produce a very important feedstock. Okay, I think it is time to make a short break. I don't know how long, 10 minutes is okay. I asked the moderator, so we'll be back in 10 minutes. And we
okay, okay, here I am. Yes, we can take a 10 minutes break.
So let's start again. So we have seen 2 examples of synthesizing typical oil products, starting instead from biomass, succinic acid and butadiene. But as I told you before, we are not obliged to do that. We can also obtain new products starting from biomass. An example is given by polylactic acid. Polylactic acid is a polymer that was never produced starting from oil. It is a typical biomass derived product with no analogous compounds obtained from oil. Again, it comes from glucose through a fermentation. This fermentation is another very popular fermentation found by Louis Pasteur in the 19th century. That is lactic fermentation. While alcoholic fermentation is produced by an yeast, lactic fermentation is produced by a bacteria, a bacillus, lactobacillus. It is the typical fermentation that occurs when we convert milk into yogurt. Obviously, for the industrial production of lactic acid, that to use milk is too expensive, but this fermentation can be achieved also using again, products from corn or linear cellulosic material. So glucose obtained by any source, cheaper than milk, obviously. In this fermentation, I recall you that fermentation must be redox neutral. In this case, there is no CO2 production, but only conversion of one molecule of glucose into two molecules of lactic acid. As you can see from the formula C3H6O3, there is two molecules of lactic acid contains exactly the same atoms as one molecule of glucose. Lactic acid is a bifunctional compound. In order to obtain polymers, we need a bifunctional compound. It is an alcohol and a carboxylic acid. Alcohol and carboxylic acid can condense to form esters, so it is possible to have a polyester. So polylactic acid is a polyester obtained from lactic acid. So polylactic acid has several advantages. Not only is derived from biomass, but it also biodegradable. It is necessary to state that these two things are not necessarily correlated. So there are biomass-derived polymers that are biodegradable and others that are not. There are oil-derived polymers that are not biodegradable and others that are biodegradable. But I must say that if we obtain a polymer from biomass, we have a higher chance that it is biodegradable because it is derived from organic matters that are in principle biodegradable. So lactic acid is biodegradable, obviously. And polylactic acid is a polyester. So in nature, there are enzymes that are able to hydrolyze ester and convert polylactic acid into lactic acid, and then is biodegradable. So it has several advantages. It has also some drawbacks. Surely it is biodegradable and biomass derived, contrary to its competitors that are polyethylene, PVC, or PET. But actually, it is biodegradable but not compostable, so it may not be used for example, for say containers that one can put in the compost. In other words, but obviously, being biodegradable can be an advantage. For example, is used for chirurgic threads because it dissolves over time in the body. But the main defect is that its physical properties are not yet as good as its competitors, and it is surely more expensive. It is impossible to be less expensive than polyethylene or PVC, in other words. But I think that there are a lot to do in order to remove these drawbacks. I don't advance, and there is still much research also in my university and my department. In my department, there are some colleagues that are working on trying to find improvements of polylactic acid, also adding additive either derived from biomass. And for example, a few years ago, an European project called Biodest has been funded, involving several universities of various countries, including the University of Genoa and my department. Here is another example of how biomass-derived compounds can be used to obtain materials or molecules that are not necessarily identical to those derived from oil. One of the most used polymers is surely PET, that is polyethylene terephthalate. Polyethylene terephthalate is a polyester formed by two monomers, a dicarboxylic acid, terephthalic acid, and a diol, ethylene glycol. Again, to form polymers, we need a bifunctional monomers because we have to attach each monomers to the left and to the right to form a chain. So in this case, we have a dicarboxylic acid and a diols. In the case of polylactic acid, we have an alcohol and a carboxylic acid in the same molecule. So it's a different situation, but again, we have a bifunctional system and we form a series of esters. Ethylene glycol is commonly, traditionally obtained from oil, from ethylene. Ethylene is a product, is an important product of cracking of oil. Ethylene is oxidized to give an epoxide, ethylene oxide, then it's hydrolyzed to give ethylene glycol. For ethylene glycol, they have found alternative ways to synthesize it from biomass. For example, from ethanol. Ethanol is produced by alcoholic fermentation. Ethanol can be dehydrated, elimination of one molecule of water to give ethylene, and then the synthesis is again like from ethylene. But there is probably a better synthesis starting directly from glucose. If glucose is hydrogenated under suitable condition, under suitable with suitable catalyst, it is possible to obtain a mixture of diols or triols, including ethylene glycol, glycerol, and propylene glycol that can be separated. So this is probably a better way because it's quite shorter, and as we'll see in a minute, to have less steps in the synthesis is an advantage from the point of view of green chemistry. On the other hand, terephthalic acid is traditionally obtained from oil, starting from benzene, that reacts with methyl chloride, which in turn is obtained from chlorine and methane, to give paraxylene, and then paraxylene is oxidized under suitable catalyst with oxygens to give terephthalic acid. It is quite challenging to obtain terephthalic acid from biomass. So a company, Avantium, thought that why do we need to prepare terephthalic acid? Can we use a dicarboxylic acid that can be obtained more easily from biomass? And the answer was yes, because it was found that if you take glucose and under chemical conditions, this is not a fermentation, under chemical condition, under acidic catalysis, you can have the removal of 3 molecules of water, affording this cyclic compound, 5-hydroxymethyl 4-fluoral. By a simple oxidation of these two arms, this compound gives a dicarboxylic acid, furan dicarboxylic acid. And so they have thought, why don't use this instead of terephthalic acid to form a polyester with ethylene glycol? And so they have developed PEF, polyethylene furan dicarboxylate. This polymer was found to be some improved properties compared to PET, and is more easily recyclable, but is not biodegradable, unfortunately. But anyway, for some application, the physical properties are even better. And so Avantium is going to build in a very big plant in Antwerp for the production of PEF, and has already some contracts with big food companies to use this as a container for food or beverages. But hydroxymethyl furfural can be used also for other applications, this time by a reduction, by reducing it with hydrogen. Hydrogen is among the reducing agents, probably the most the cheapest, the most easy to be used, not the cheapest, but one of the most useful. Hydrogen can be obtained at the expense of energy from water. With hydrogen and catalyst, you can reduce the aldehyde to the alcohol and the 2 double bonds to obtain this intermediate that then, going on with the hydrogenation, also these 2 bonds are broken, and one obtains 1,6-butanediol. 1,6-butanediol is a diol that can be used also in polymer chemistry. For example, by reaction with dimethyl carbonate, which is in turn obtained from carbonic anhydride and methanol, it is possible to obtain a polycarbonate that is used as component in some kind of polyurethane. But 1,6-butanediol can be also oxidized to this lactone, epsilon caprolactone, which is the monomer for an important polyester called polycaprolactone. And even more useful, by reaction of caprolactone with ammonia, one obtained epsilon caprolactone, which is the monomer for the synthesis of polyamide. Polyamides, in particular, polyamides are typically called nylon, and from epsilon caprolactam, one obtains nylon 6. So you can see how this product coming from glucose, this time with no fermentation, can be useful in preparing building blocks that are used for the synthesis of, again, compounds that are already known starting from oil. Okay, but in developing new chemical processes formed by biased molecules polymers, we must also be sustainable. So it is also important that the processes that we develop in this new organic synthesis, starting from biomass, adhere to the principle of green chemistry. The principle of green chemistry has been enunciated about 25 years ago by Anastas and Warner and are listed here. I don't go through in reading them all, but I must say that these 12 principles for three, in my opinion, three great goals. One is planet health, so to reduce waste, to reduce consumption of energy, and these are written in red. For example, atom economy. Atom economy means ideally to waste as little as possible of your reagents. So in the idle synthesis, you all the atoms of the starting material goes into the products without using steps that add more atoms that later are removed. Energy efficiency, so also the chemical processes can be energy consuming. So it is better to favor processes that don't need energy. And I will show you that enzymatic processes have this great advantage. Use renewable feedstocks. We have seen use renewable feedstocks. This can be very good for the planet, and also step economy. So if we reduce the number of steps in a synthesis, this means reducing also the use of solvents and of other materials that maybe can be recycled, but you always lose something. And then this is in line with atom economy to use catalysis instead of stoichiometric reagents. But also the principle of green chemistry have the goal to have less pollution. These are not necessarily the same, because planet health, I mean, avoid the excess of carbonic anhydride release in the atmosphere. Less pollution means pollution in the nearby in the territory near the chemical industry, and safety relates to possibility of accidents. In particular, I will show you this 12th principle. Substances and the form of substance used in a chemical process should be chosen to minimize the potential for chemical accidents, including release, explosions, and fires. And I will show you an example of application of this principle. This principle has been enunciated in 1998, but the worst chemical disaster in the world, in the history of the chemical industry, is surely this one that happened in 1984 in Bhopal in India and led to nearly 4,000 casualties. The problem was the factory was quite new, modern, and with the safety measures and so on. And it was meant to produce this compound. This compound is an urethane, is a derivative of carbonic acid, and was used as pesticide. Was used, but is still used. So it's not an old compound, it's an urethane. The traditional way to synthesize urethane is to react an alcohol or a phenol, in this case, with an isocyanate. The isocyanate is a compound where we have a double N carbon bond accumulated with another double carbon oxygen bond. Methyl isocyanate is a gas highly toxic and is prepared from methylamine by reaction with phosgene. Phosgene is another gas highly toxic. Again, application of chlorine, because phosgene is quite widely used in the chemical industry. Why? Because it can be very easily obtained from carbon monoxide and chlorine. The problem was that they produced a large quantities of both phosgene and methyl isocyanate and stocked them instead of using it once. And when there was a lowering in the market for the final product, Carbaryl, the company stopped production. The safety measurements were enlightened, and so the accident came. But surely there were several human errors in this accident. But from the point of view of the green chemistry principles, the focus should be on the wrong overall design, not the fact that there were human errors, because the design should be made in order to avoid errors. So I will show how the problem was later solved for the synthesis of the same compound. First of all, phosgene is no longer accumulated. It is produced from carbon monoxide and chlorine, but it's produced and immediately reacted with the phenol to form this chloride that then is immediately reacted with methylamine for the final product, which is less dangerous. So as you can see, no methyl isocyanate formation. So they avoided the formation of methyl isocyanate, and they produce phosgene, the other dangerous gas, in continuous without accumulating it. So these principles should be kept in mind. And I will speak now of another important class of polymers that have some problems from the point of view of green chemistry, that are polyurethanes. Polyurethanes are quite useful. Here are some products, mattresses, foams, and also insulating panels for increasing the thermal efficiency of our house. These polymers are obtained by reacting a diol, again, we need a difunctionalized system, with a diisocyanate, so a double isocyanate. Okay, this double isocyanate is not so dangerous as methyl isocyanate or bofal, because methyl isocyanate is a gas. These are not gases, but anyway are toxic, cancerogenic. And moreover, they are prepared traditionally from diamines and phosgene. Again, phosgene, which is toxic and dangerous. So some people are thinking, how can we have a more sustainable synthesis of polyurethane? So starting maybe from biomass, or also using less dangerous processes. Here I will show you an example. The first thing is to avoid the use of isocyanates. So they have found that urethanes can be obtained by reaction of diamine with the double cyclic carbonates. So no isocyanate, less dangerous and less toxic compounds. In this case, obviously, one obtains a polyurethane slightly different, having also hydroxy group in this position, but they are useful anyway. And in order to obtain this carbonate, there are two ways. One less green and one more green. The one less green is oxidation of a dialkene to give a tetraol, a tetraalcohol, and then formation of the cyclic carbonate, again using phosgene. But an alternative that was found is, which is much greener, is to oxidize to the bisect epoxide and then treat the bisect epoxide with carbon dioxide, carbonic anhydride, with a suitable catalyst to afford directly the bicyclic carbonate. So in this synthesis, no phosgene, no isocyanates. So it's greener, but the starting material is from oil, is a diene. So what they have thought is, can we synthesize polyurethanes from biomass? And in this case, they looked at another important biomass component, lignin. Lignin is a component of wood. together with the cellulose and hemicellulose. Lignin is much more complex than cellulose and especially is more difficult to break, but they have developed several thermal, chemical, and enzymatic methods to break lignin and to obtain some interesting aromatic compounds that contain this OH group, that is the phenol group. These phenols can be, as I will show you later, interesting. And in particular, these researchers have thought that using some of this phenol coming from lignin, especially guaiacol and vanillic acid, they could synthesize bio-based polyurethanes. So they have taken guaiacol and vanillic acid and condensed together using a Friedel-Crafts alkylation. This Friedel-Crafts alkylation works because under acidic conditions, this OH group goes away, forming a carbocation, and then the carbocation reacts with guaiacol. For those who knows more of organic chemistry, guaiacol is activated, highly activated to electrophilic aromatic substitution, and so this reaction can work. And they were able to obtain a symmetric, starting from two different starting materials, they obtain a symmetric diphenol. And then they converted this diphenol into a diamine by an SN2 reaction, a Williamson esterification, followed by a Smythe's rearrangement. So this is a good way to substitute the OH of the phenol with the nitrogen. It forms a bisamide that can be, under this condition, hydrolyzed to give the diamine. And then they converted the diamine into the diisocyanate with the 4-gene-free method. So in the last years, they have developed method to convert diamine into isocyanates, not using 4-gene. So this is quite good. Okay, now I will tell you something about my own research. We have been interested in the last 20 years in my research group in multi-component reaction. Multi-component reaction can be considered a green approach to the synthesis. In a typical synthesis, if you want to prepare a compound where you have a central scaffold and some decorations that are substituents of different kind, you must adopt a serial synthesis with a number of steps, and in each step you add a further piece of your final product. This is sometimes problematic because the number of steps can be even higher than those what shown here, because you have to protect the protect functional group. On the other hand, multi-component reactions are designed in order to join 3 or more, for example, 4 in this example, 4 pieces in just one step, in one reaction. In this way, we can prevent waste, we will have atom economy, energy efficiency, because usually multi-component reaction works at room temperature, and also obviously step economy. This is a quite potent methodology that has been used, especially in combinatorial chemistry, because if you join 4 pieces, you can change the decoration and in a very fast way obtain a collection of different compounds. And obtaining a collection of compounds in a combinatorial manner is a very important strategy in order to synthesize a lot of molecules to be tested, for example, as drug candidates. Especially in pharmaceutical chemistry, in drug discovery, it is important to have techniques that allows you to synthesize many different molecules in a short time. But the last 7-8 years, we have been interested in applying multi-component reaction that are considered, as stated in this review, are considered a green methodology to bio-based feedstock. So, for example, a possibility is to use levulinic acid. Levulinic acid is another bio-based compound that can be obtained by glucose. Again, through the intermediacy of 5-hydroxymethylfurfural. This compound comes from dehydration of glucose, but it is possible under acid catalysis perform a partial rehydration, adding 2 molecules of water with a complex mechanism that forms levulinic acid that has only 5 carbon atoms plus formic acid. So 1 carbon atom is lost in this process. Levulinic acid is a bifunctional compound that has been used, for example, in polymer synthesis. But our idea was to use it in a combinatorial multi-component synthesis of drug-like molecules. So molecules, bicyclic systems containing 2 nitrogen that are typical scaffold for possible potential drugs. So we developed a fast synthesis in 2 steps of a collection of compounds, of this kind. This is based on a multi-component reaction where levulinic acid, an amino alcohol, and an isocyanide are mixed together. So you see 3 components. So it is a 3-component reaction to form this compound. And in the first step, in the second step, there is a cyclization of this nitrogen onto this carbon with elimination of water to form the bicyclic system. So we can perform this reaction introducing 3 diversity inputs, R1, R2, and R3, and so we can have a collection of products. This is a possible approach of multi-component reaction on a bio-based starting material. But we were also intrigued by the interesting properties of natural polyphenols. Natural polyphenols are well known. Some of them, for example, resveratrol, which is contained in the peels of grapes, of red grapes, are known to have anti-aging, anti-inflammatory activity. The same like curcumin or epigallocatechin gallate. Whereas hydroxytyrosol, a more simple polyphenols, which is contained in olive meal wastewater, has also some interesting pharmaceutical properties, and we are also working on this, but I will not tell about that. So our idea was that natural polyphenols are not very stable in some cases. They have not idle pharmacokinetics properties. So although in vitro they show interesting properties, in vivo maybe these properties are not so high, and this is not easy to modify them. So our idea was to take advantage of products coming from lignin, like this one, so simple products, and join them through a multi-component reaction. So the idea was to take 4 components, each one containing or not a phenol, joined together after functionalization through a Unige multi-component reaction in order to obtain a series, a collection of compounds characterized by a central scaffold and by substituents containing various phenols. This is an example of what is called a fragment-based drug discovery approach, where we join small fragments to a more complex molecule in order to understand which combination is the best. So this idea was fortunately funded by Fondazione Cariplo. The project was called From Bioinspired Molecules to Alzheimer's Disease Prevention, and was funded by Fondazione Cariplo by a group composed by us, by CNR, two centers of CNR in Genova and Milano, and the Istituto Mario Negri in Milano. And after synthesizing a series of this compound, we were able to find the best one, which has this formula. And we found a very interesting result. I will try to explain. These compounds, a series of mice were inoculated were injected by this compound alone, and we saw no difference. Or else were injected with amyloid protein. Amyloid protein is considered to be the main responsible of Alzheimer's disease. So what these bars means is the capacity of the mice to recognize new objects. So the mice, if they had a good memory, understand which objects are not new to them and those that are new, and they preferably go to the new ones. So when the mice is injected by beta amyloid protein, you see this result. It loses soon the possibility to recognize new objects. So there is a great loss in memory. But if we treat the mice with beta amyloid protein and together with our compound, you see with the 10 macromolar concentration, the mice behaves like the mice that was not treated with the beta amyloid protein. So it is an interesting result. Obviously, to arrive to a drug is a long way because the problem is to vehiculate this compound to the brain. That is not quite very easy. But these results show that the approach was promising. So an approach where we can join natural derived compounds in a fragment-based approach to form new drugs that are not natural. This compound is not natural, obviously, but they can mimic natural polyphenols and maybe can have better properties. Another study that we have carried out in our group during this big project, we found out, as you can see, a component of this compound, which was the best one, the one in green, is ferulic acid, which is a product that can be obtained from lignin, but also this one, but also from other plants. It's quite ubiquitous in various plants. And during that work, we found out that if we have a tertiary amide of ferulic acid, but this does not happen on ferulic acid itself or on esters of ferulic acid, but with the tertiary amide, by irradiating at UV at 350 nanometers, but even at with the solar light, at least less efficiently, we can obtain a complete isomerization of the double bond. This double bond is in an E configuration. You see this group and this group are opposite, and it is isomerized into the Z configuration. Obviously, as you can see from these formulas, the form of the molecules are quite different. So they will have different properties from physical properties to also biological properties. So we are now carrying out studies in order to explore the possibility to use this trick, for example, for photoresponsive polymers. So think about the synthesis of polymers containing this structure. And by simply treating with light, the polymer can change its form and so change its features. So a photoresponsive polymers. And also we can have drugs that are activated maybe in the E form and not in the Z form or vice versa. So we can have the possibility with light to activate a drug that is not active or deactivate a drug that is active. Meanwhile, we have found that these lipids, these amides have also lipid lowering effects, stated in this publication in collaboration also with the biologist of DISTA. So, as you can see, while in the first years the main focus was on using biomass to prepare fine chemicals that are obtained in a huge amount, so low value, high amount. Now, even more and more people are trying to explore the possibility to use biomass-derived compounds, not only to obtain commodities or fine chemicals. Commodities are the building blocks. Fine chemicals are chemicals that are obtained in a huge amount with low cost, to convert them into high-valued chemicals. And obviously, like drugs, cosmetic, and functional materials. And in doing so, using green synthetic methodologies. So this is the future sustainable organic synthesis, not only to obtain commodities and fine chemicals from biomass, but also high-value chemicals and using green synthetic methodologies. So we are trying to do this all. And for this approach, biotechnology can have a great importance, in particular, white biotechnology. What is white biotechnology? Biotechnology is typically divided in three realms. Red biotechnologies are dedicated to drugs or biochemical devices. Okay, it's in Italian, sorry. Are those that are used for producing drugs or biomedical devices, like, for example, biotechnological drugs and so on. Green biotechnologies are devoted to agriculture, so they are the modification of organisms for improving crops and so on. White biotechnologies, so red biotechnologies are red because of blood. Green biotechnologies because they're used in agriculture, and white biotechnologies employ enzymes or microorganisms for organic synthesis, and are called white because usually lyophilized enzymes are white powder. So I will concentrate on white biotechnologies. I'm working in this field since 1985, and so I think to be one of the first Italians to work in the field of white biotechnologies applied to organic synthesis. So I like very much this field. The use of enzyme or microorganisms brings about several advantages according to green chemistry principle. First of all, usually with enzymes, the solvent is just water, so safer solvents prevent waste. Enzymes are catalysts, can be recycled, and are often very selective, so catalysis prevent waste. Reactions are typically carried out at room temperature, so there is also energy efficiency. Enzymes are not toxic, and they are biodegradable, surely. So less hazardous chemical synthesis and biodegradability. So they can be recycled, obviously, but if they are not, they are biodegradable. Selectivity of the enzymes allows to avoid the protection steps. So also there is an advantage for step economy. And enzymes and microorganisms, where even if they cannot do everything, as we already seen, may be optimized using genetic engineering techniques. There are some drawbacks, obviously, because enzymes are selective, but this can be a drawback because being selective may not work well with substrates, so they can work while chemical reagents work on every compounds. Typically, enzymes may work on some substrate and not on other substrate, being selective. But as I told you, using genetic engineering techniques, this drawback can be overcome. Enzyme microorganisms can be used only in a limited temperature range. They cannot be used at 200 degrees, for example. And then not all organic reactions are natural, and thus not all reaction can be catalyzed by enzyme. But also this drawback is somehow, there are some examples to overcome this drawback, because enzymes are sometimes efficiently used for reactions that are not the natural ones catalyzed by this enzyme. Well, I want just to show you an example. Obviously, the most used enzymes are hydrolytic enzymes because they don't use cofactors such as esterases, lipases, proteases, as well as they are available low cost and so on. But recently, more difficult enzymes are becoming more and more important. Then I will focus as an example to aminotransferases. Why aminotransferases? Because, as I told you, it is important, especially in the synthesis of drugs, to be able to introduce nitrogen into molecules. And biomass-derived molecules usually have oxygens, but not nitrogen. And a very useful way to do that is reductive amination. Reductive amination is the conversion of a ketone into an amine by reaction with ammonia and reduction at the same time. Obviously, can be done chemically, but methods used for chemical reductive amination often are not very green and are not very selective. So it will be very useful to use aminotransferases, but aminotransferases are enzymes that actually are used in nature for redox neutral synthesis of amino acids. So, for example, if you take this ketone, the anion of pyruvic acid, it can be reductively aminated to give alanine. This is a reductive amination. But the enzyme that catalyzes this reaction is redox neutral because at the same time, the same enzyme in the same process using this compound pyridoxal phosphate as catalyst perform the opposite reaction on another amino acid, which is typically glutamic acid, which is converted into a ketone, alpha ketoglutarate. So the enzyme performs a reductive amination at the same time oxidative deamination. So if we want to use this enzyme for this reaction, we need something that is oxidated through an oxidative deamination. But the main problem is that this reaction in nature is used typically on alpha keto acids. It's not used on any ketone. So unnatural substrates may be not reactive at all with these enzymes. This is a problem of enzymes. I remember an old professor when I was a student once told us, I had a great idea. The problem with enzymes are that they are too selective. So we can enlarge the active site of the enzyme. And obviously all the people who ordered this idea were laughing because how can you enlarge the active site of the enzyme? Well, now they have succeeded. They have succeeded in enlarging the active site of the enzyme. This is an astonishing achievement because the need was to convert this ketone into this amine. This is one of the most important drugs that went in clinical use in the last years. Sitagliptin, that is for diabetes. But the problem was how to convert this, creating a stereogenic center and obtaining just one enantiomer. And as I told you before, with aminotransferases, you need to use something that is oxidated, and they use isopropylamine. But the problem is that a collection of a huge collection of enzymes they had, no one was able to give any conversion on this ketone. So what they did, they used a truncated ketone, a simplified ketone, and after some effort, they found an enzyme that was able to react, although very, very slowly, 2% conversion after 1 week. And then the large pocket of this, the active site was rationally modified. So they changed the active site of the enzyme. How? Through a site-directed mutagenesis, a technique where they can change an amino acid of the protein, a single amino acid. And then the first phase was done rationally. Then there was the optimization was made combinatorially using evolution-like evolution. So evolution rounds. So they change randomly and they found the best enzyme. Then they change again randomly. And at the end, they were able, after 11 evolution rounds, the final enzyme had 27 mutations compared to the wild one, was 4,300-fold more active, and was tolerant to extreme reaction condition. The reaction was carried out in 100 grams per liter with 1 molar isopropylamine, which is the amine that is oxidized to acetone, with 40% dimethyl sulfoxide in water at 40 degrees. And the compound was obtained with 99.7% EE. So isopropylamine undergoes oxidative deamination to give acetone. Okay, more recently, they have applied a similar strategy to, this time, a bio-based substrate. Again, starting from lignocellulosic waste containing glucose, it is possible through pyrolysis at high temperature to obtain this interesting compound, levoglucosenone. Levoglucosenone can be hydrogenated to styrene, which is sold by a company in Australia as a bio-based solvent. And the same company succeeded in performing a reductive amination here. It was less problematic than the previous one to obtain this compound. Interestingly, chemical reductive amination gave the opposite diastereoisome. So this selectivity could be achieved only through enzymatic reaction. And this compound was then opened and converted into a new drug called nemtabrutinib, a drug that is going into market in few in a little time. So, in other words, white biotechnologies and bio-based starting material can be used not only for high volume polymers, but also for active pharmaceutical ingredients. So, as a recap, I will show you the versatility of glucose. We have seen in this lecture that glucose can be converted by fermentation into ethanol, 1,3-butanediol, lactic acid, succinic acid, and by chemical means, it can convert it to levoglucosenone, hydroxymethyl furfural, which in turn can be converted into caprolactam, caprolactone, and levulinic acid. So a lot of building blocks, all obtained from the same molecule, glucose. And I conclude with this slide. So biomass from the sea. I searched in the literature, but actually the sea by now has been useful in affording some polymers, natural polymers, like for example, chitin, which is quite abundant in the sea. You see, compared to cellulose, chitin contains 1 nitrogen. Chitin is typical, the structural molecules that forms that is present in crustacean. And by chemical deacetylation, it gives chitosan, which is very useful in several applications. And also alginate that comes from algae is used for applications in industry, but also in cosmetic field. Apart from polymers, I didn't find many applications of biomass from the sea, but I will show you a molecule which is quite interesting, a red molecule, astaxanthin, that can be also produced by algae, and is the responsible the color of shrimp. Shrimp have this color because they eat algae that contains microalgae that contain astaxanthin. So this is a quite interesting molecule and can be an example of organic molecule that can be used for organic synthesis. Okay, I finished in time. I thank you very much for your attention, and here are all the sponsors of the courses. And obviously, I'm ready for any question